All right, so here we are at an example where we would like to find out, where we would like to apply our understanding of the definite integral into finding work for here. So let's spend some time reading the worded description of our problem here. So what it says here, the force on a particle is described by 3x squared plus 3 at a point x along the x-axis. Okay, we would like to find the work done in moving the particle from the origin to x equals 9 right here. Okay, so a couple of highlighted information can be recognized here. So obviously the question is asking us to find the work done. That's what it is, and specifically the work done in moving the particle. So just like how I explained that in the general discussion earlier, prior to delivering this example, then it's all about anytime we're calculating work, it's because we're moving an object. We're moving this particle, right, from a place to a different place right here. So this phrase right here is indicating for us that we have a distance. We're moving a particle from the origin on the x-axis to x equals 9. Okay, so we have a distance to move. And so in that way, we have a distance, and now force is given right here. And we will be jumping even further into that. All right, so now that's what it is. We want to find out, we want to calculate the total work done in moving the particle from the origin to x equals 9. So we already realized right here that we have a distance. And then we have force. All right, so now let's start breaking down the problem right here. But this is what I would do. So I'm going to try to pass it down to anyone studying this from me right here. So we are going to apply the definite integral into calculating the total amount of work done. So just like how I emphasized that concept in the general discussion prior to stepping into any of the actual example, okay, then to calculate total work, we think about we're accumulating all the little work amount. So dW in my explanation throughout, after viewing the general discussion prior to watching any of these examples now, then dW here represents the little amount of work. Okay, little work amounts. So any dW amount right here is a little work amount. And so to find the total work, only one fundamental. To find total work, we have to accumulate all little work amounts from some start to some end right here. Okay, and so keep referring back to that, to a couple of explanations, actually quite a few explanations back in my general lecture, to point out for you that what I purposely emphasize here is that anytime we're calculating work, we are going to be accumulating, and that's where we want to see, that's where we actually see we can apply the definite integral into calculating work, because it's accumulation. We want to accumulate all the little work amounts from a start to an end. Just that. Keep that reminded, and keep that in your mind right there, and keep reminding yourself about that. We're accumulating all the little work amounts from a beginning to an end. Okay, and so now from that way, we're going to start, once we start reminding ourselves about that, let's start breaking down the situation according to the description given in the problem. So we're on the x-axis. That's what it says here. That's what it said here. So at a point x along the x-axis, and actually let me clear out all of these highlights here, and let's focus on what we need right now. So we know that we're on the x-axis at a point x along the x-axis. Okay, and so now quickly let me draw the situation. And I don't even think we really need to draw the y-axis here, but see, just for us to know this is where the origin is. And then so at any point on the x-axis, so at a point x right here, this is the x-axis, and then at any x value on that path like that. Okay, so the idea is, so think about this infinitesimally small particle on the x-axis as we're moving it along. As we're moving it on the x-axis here, then at different points, the force, you see, it's all about force exerting. So now we are right into that business right there. We're pushing an object. An object it doesn't always have to be big. This object here is a small object. It's only a an infinitesimally small object. It's just a single point on the x-axis. Okay, but now as we move that particle on the x-axis, the amount of force we apply on that, the amount of force we're exerting on that is changing. And so now it's not a constant force. See, just like how it was, just like how I described that in the general lecture. And now you realize that the force here is given. We don't have to question how the question came up with that, but the force here is a function of x that depends as following: 3x cubed plus 3. That means from where the origin, from where after it leaves, after the particle here leaves the origin, as it starts making some x distance. How's that? So here's the particle, but as the particle being pushed x distance away, the amount of force changes depending on how far that point is, based on this formula: 3x cubed plus 3. 3x cubed plus 3. So this function right here generally represents our force amount at any single point where our particle is at, after making some x distance away from the origin. All right, and so now you can see that it's a clear phenomena here. It's a clear situation here where force is changing. Okay, and so now, where's the path? The problem is asking find the work done. Find the work done. Now I'm going to put back the highlights here. Find the work done in moving the particle from the origin to x equals 9. Okay, so moving the particle, but now the origin to x equals 9. Those are the information that should catch our attention by now. Okay, so 9 is maybe some final destination here, but 0 is the origin is right there. So that object right here, it doesn't have to get larger, but the idea now is that for some reason, that's why, as I said earlier, we don't need to question how they came up with this force formula. But here at each different distance that we have made, right, or at each different point on the x-axis, the force amount changes. That's what it is. Okay, and so now here's how I see it. Think about infinitesimally. Let me write. So force right at that single instance, f of x, capital F of x, is a 3x cubed plus 3. But think about as we push that particle completely along the path here from the beginning to the point. It doesn't even have to be a curvy path. It's just one straight path. But what's already happening here is that so much force changing, and it's changing through infinitely many single instances throughout that path. Okay, and so now you can start thinking about, so how do I see the little amount of force? How do I see the little amount of work right here? Just think about when you push from one point to infinitesimally small, this small little change right there. That's one little change in distance, because we change from a location to a different location, and then we go from 0 to 9 right here. So at different locations, right? So this change right here is infinitesimally small change in x, but that now can be regarded as a distance. And so that distance, the amount of force undergo there is different. And so we can just multiply force with that dx right there, and then in a different instance, at a different small change, a different dx right there. And so in the end, now that you have learned about calculus, dx, all of those d values are all about the infinitesimally small changes. So that means this is still even too big. Just a small change, a change so small that even only a pencil stroke already tells there's a slight change in the distance. And so now what I'm seeing here, on each little amount of force is simply the function or the force amount at that x instance multiplied with the dx. See, so this is distance times force right in this problem. Okay, so at each instance, just think about it. The distance is so small to the point that we can't even tell the two different x points on the x-axis anymore. But there's different force changing in a small distance, and that small distance there, we call the dx. Okay, we call it dx, and then we multiply the amount of force on that. So force times the small amount of distance. That's the small or the little amount of work, the infinitesimally small amount of work. All right, and so now, once we have that, now here's our concept right here. We're accumulating so allow me to rewrite this a little bit. So all of the little dw right here is the same as 3x cubed plus 3, the force at any x instance, but multiply with the infinitesimally small change in distance. That's what this is. Okay, and so in that way, now I'm going to be accumulating start to end. The problem here is making it quite clear about the start to the end right here. Now, I have mentioned about this when we begin our journey into integral problems, but see, our d expression here is a dx. It's just in the way it is. It's explained right here in the picture. Our d is a dx. So let's check for a consistency before I throw in the start and the end value for our integral over here. But the function, is the function here on behalf of the variable consistent with this x right here? Yes, it is. It's a function of x. So it's consistent with the dx. So we're all good now. So that means our start and our end here has to be those values in terms of x as well. So now clearly speaking, from 0 to 9, the beginning to the end of the path like that. All right, so now we have successfully set up our integral. Our total work will be calculated as the accumulation of all the little work amounts from the start to the end, translating that into the actual problem in this situation. Now that's what we have here, a function 3x cubed plus 3 multiplied with dx, and we're accumulating all of that. So this part here is the little work amount, accumulating all of those from 0 to 9, because here, see, the beginning of our accumulation happens when x equals 0, and the ending of our accumulation happens when x equals 9. That's why we're accumulating like that. All right, and so now at this point, we are ready. And of course, needless to say, this video is, this lecture, this understanding, this video you're viewing here is highly recommended to be viewed after you understand what the fundamental theorem of calculus is, because I am going to use that for finding the answer to this definite integral. So what we now have here is a definite integral. Okay, so now the fundamental theorem of calculus says all we do is just find the antiderivative there, which gives me now 3/4 x cubed plus 3x. And I am going to evaluate that antiderivative there from 0 to 9. All right, and so the work here comes out quite easy. So it's 3/4 times 9 cubed plus 3 times 9. This is the antiderivative evaluated at 9, the upper limit of our integral. So starting at this point, once we have successfully completed our integral setup, then we treat that problem completely as a definite integral problem, where we have our freedom to use the fundamental theorem of calculus, provided you already knew what the fundamental theorem of calculus is. Okay, and then so now I'm going to subtract. And even with this little amount of space here, I can still even do the work here, because 0 substituted into all of these terms, where each one here is all an expression of x, so it's all just a 0 out when we're substituting 0 into this entire antiderivative. All right, so in that reason, our final answer, 4,942.75. Okay, and this is joules. Okay, so I got to allow me to clarify the units a little bit right here. Allow me to clarify the little bit of units. This problem, I admittedly, this problem went a little loose in terms of the units, but so any distance here is measured in terms of meter. Okay, so x is in meter. Okay, and then capital F of x, okay, is in Newton. So I'm staying with the standard units for now. Right, so capital F of x is in Newton. So just like that, force times distance. But things here go a lot more advanced in that. It's not one constant force going through one constant distance. It's the kind of force that's constantly changing, that's continuously changing as described by this function. And that's why we're accumulating all the little amount of work. Little amount of work meaning we underwent through infinitely many subsections. And each of these little sections, we have to keep letting it smaller and smaller and smaller. Okay, and that's how it's done. So for this particular example over here, the force, so now it makes sense that the ending final answer here is in joules right here. 4,942.75 joules.